In this video we're going to look at how sound is represented inside a computer. Sound representation falls in part of the same topic as data representation. Now we talk about sound or light as being either analog or digital. So in order to start thinking about how we get our sound into the computer, it's about thinking about what sound is. And sound is pressure in the air, it's vibrations, and the human ear interprets these vibrations and this sound and turns this into electrical signals that the brain uses. So let's have a think what sound's like. Sound, as we can see here on this diagram, could be thought of as like a wave. It continually varies, so you can't put an exact value on it. So it infinitely varies, it continually varies, and it's said to be analog by nature. In terms of light as well, the light that we see, light has a specific wavelength, and again that is classed as analog. Think of the term analog as well. You might go back to an analog record player, and the music that you are hearing from a vinyl is analog. The needle reads that sound and interprets that into vibrations. We might think of analog as being able to go along across lots of different values, so you're not just stuck with 0 and 1, but you've got the infinite values in the middle, 0.2764 or so on. So analog is said to continually vary, and we can draw an analog wave to show what analog looks like. That versus digital. Digital goes up in discrete steps, for example on or off, 1 or 0. Steps such as 0, 1, 2, 3, 4. If you think of a digital volume control, digital volume will be set at volume 2, volume 4, volume 8. If it was an analog volume control, you could turn the dial to be between two values. Temperature is something else that we can represent in analog formats, because the temperature in the air is never exactly 22 degrees. It may be 22.12758, for instance. If we've got an air conditioning unit, we may be able to set the temperature in 1 degree units or half degree units. This is classed as digital, so we can see the difference between our analog and our digital. Computers use digital data. Any electronic device uses digital data, and that's because of how we store data inside, like the binary number system. So we need to somehow get nature's data, which is analog, and get that into being digital. And in order to do that, we use an analog to digital converter, an ADC. For example, in a computer we might have a microphone. So sound is basically pressure in the air, it's vibrations. The microphone, also known as a transducer, takes that sound pressure and the vibrations and converts it into an electrical signal. So that's the first step that the microphone does. This then gets converted from an electrical signal through an analog to digital converter, an ADC, and that turns that into discrete steps, into digital signals. We also have digital to analog converters. So this converts digital signals from within a computer to analog using a DAC. So the sound that's in an MP3 file will be encoded using the binary number system, and these binary values are interpreted. The digital data is sent from the file from the computer to the digital to analog converter. That is then converted into an electrical signal, and the electrical signal causes the speaker to vibrate, and this is what then causes the analog sound waves to come out of the speaker, and us as human beings are able to interpret that sound. In this case, the speaker is a transducer. So that was the difference between digital and analog data. Now we've got a particular type of device known as a MIDI device. MIDI stands for Musical Instrument Digital Interface. And this can take data from a musical instrument and store it by digital means, such as using an acoustic guitar. We can take the MIDI device, we can place it under the strings, and when the guitar is played and the strings vibrate and cause a sound, the MIDI device will pick up these sound waves and they'll convert them into digital form. Now, MIDI files tend to use event messages, and they control various properties of the sound, and these messages get encoded in binary, and they allow us to provide communication between the MIDI device or between a MIDI device and the processor. An event message may contain data on the following: when to play a note, when to stop playing a note, the time in a note, could be the pitch of the note, how loud the note is, the effect to use when playing a note, what instrument that note is. And we can actually start to take this data and create a MIDI file on the computer. MIDI files can then be used by a number of different MIDI devices, like a MIDI keyboard, in order to be able to interpret the MIDI file and play a song, or a file to contain lots of different interpretations of instruments, and each different instrument could be assigned digitally, and therefore a sound file can be recreated. I'll show you an example. Here is a simple program. Now this contains the notes, the length of the notes, the type of notes they are, so we've got the sheet music there to represent it, and here is the digital form. Now what we may have here in terms of this is the piano, and say for instance this note relates to that key, and it shows the timing of this. It allows you to digitally edit a song as well. So if you was to record a song on a piano using a MIDI device, it would record each note individually into a program on a computer. If you wanted it to be perfect and your timing is slightly out on the notes, then we can digitally remaster this MIDI file by moving these blocks to be within the correct timing. If you've hit a dumb note, we can delete that, and if you then wanted to apply a different type of piano, we can see here, not very clearly, but you can change the instrument. Now we can have lots of instruments, and the MIDI file doesn't record the actual sound, but the MIDI file records the notes and when to play them. Advantages of MIDI files: they're much smaller because you're not actually recording the specific sound. They therefore require less memory and therefore load faster. Therefore there's a benefit to embed them in web pages. We can edit them, just as I've explained there of what we do, and we can support a wide range of instruments. People may use MIDI files when they're said to remix a song. This type of file is used for creating dance music or any kind of music in which we want to digitally create that music. Sometimes we want to record the actual sound. So for instance we want to record somebody singing in a microphone, or we want to record a band playing, we want to record an orchestra. So at the moment, as I'm speaking into this microphone, I'm wanting to record this. In that case we have to use sound sampling, and this is the process of converting analog sound waves into digital form, and this creates what we call digitized sound. So as I've referred to earlier, this is ADC conversion. Analog sound waves, they're infinitely variable. The sound wave's amplitude must be measured at fixed regular intervals, and this measurement is then said to be quantized, so that's taken to its closest point on the y-axis, and that's converted into binary form. We don't record all of the sound, hence the term we sample. We have a sampling rate, so this is the number of samples taken per second. We have a sampling resolution. This is the number of bits allocated to each sample. In this case there are 3 bits allocated to each sample. In case of sound file sizes, if there are 10 seconds of mono audio, there's a sampling rate of 500 Hz, a resolution of 16 bits. How many mics will be stored? 10 times 500, 5,000 samples, 16 bits is 2 bytes, and therefore 2 bytes times 5,000 gives us 10,000 bytes. Divide by 1,000 gives us 10 kilobytes. So that is a video talking about analog and digital sound, talking about MIDI and its use in sampling, what sampling is, and a quick tour through sampling rate, sampling resolution and estimating file sizes. So just to go back, remember sampling rate is a frequency, it's measured in hertz. The number of samples taken per second. Sampling resolution, the number of bits allocated to each sample, and through knowing both we can work out the estimated file size. If this was stereo sound would use 2 channels, one for the left ear, one for the right ear, so you would multiply the final amount by 2. Thanks for listening.